Talk about a work on the equality of a positive mass theorem, and I will begin by writing the statement of our theorem. So we will let Ng to denote a Riemannian manifold complete unbounded. Which has a symmetric 0-2 tensor denoted by K. And we'll assume the following four assumptions. The first one is a dimension of a Riemannian manifold is between 3 and 7. And the second assumption is this triple is asymptotically flat. So which means the Riemannian manifold, the N outside a compact set is diffeomorphic to Rn with the ball removed. So that's topologically is flat. And also in the exterior region, we assume the matrix behave like a Euclidean matrix. And the K, the symmetric 2 tensor goes to 0. So at manifold infinity. And then we have a sort of curvature assumption. So we'll require, so it's so-called the dominant energy condition. Which says the the scalar curvature of G is bounded below by some function defined in terms of G and K. Right, so this term is the norm of these two tensors, and that's the trace square. And this is the one form by taking divergence and minus d of the trace k and taking the norm with respect to g. So this is so-called dominant energy condition. And the last assumption we have is for this class of manifolds, one can define so-called the ADN energy and ADN momentum. So the ADN energy is just a number which we denote by E. And the linear momentum, which is another invariant, we denote by P. That's a constant vector. And we assume those numbers and the constant vector satisfy this equality. So the conclusion we have is the only possibility is all those invariants E and P are identically 0. So those are invariants. So the ADN energy is the ADN mass, which mentioned in yesterday's talk. So as a consequence of our theorem, we can actually conclude this Riemannian manifold can be isometric embedded into Minkowski spacetime. Which is one flat Lorentzian manifold of one dimension higher. And the K is the induced second fundamental form. So in some sense, this theorem is a rigidity statement for a way to characterize the flat Minkowski space-time. So in fact, if it's embedded in Minkowski space-time as a Riemannian manifold, the only possibility is actually a graph in Minkowski space-time. So if we write this coordinate we call t, the vertical one, and just schematically denote the horizontal direction to be the remaining n direction, the Minkowski space-time has a matrix which is minus in the vertical direction. Right, so the only way for some manifold to embed it as a Riemannian manifold is if it's as a codimension 1 hypersurface Riemannian. The only way is it must be a graph. Okay. So one of the probably difficulty in proving this theorem is we are not actually really working on the rigidity of this triple n, g, and k itself. Because you can draw any graph in Minkowski space-time. Log graph with the induced matrix and induced second fundamental form will satisfy all those 4 assumptions. So it's the rigidity for the space-time, but we don't want to work on anything on the space-time because a priori we don't really know if it's inside any space-time. In other words, another difficulty translating in other language is we don't really know in proof of theorem to demonstrate what geometric quantity should vanish, flat in what sense. Okay, so let me make a remark or couple remark. The first one is this statement, to my knowledge, was first conjectured by Wheaton, at least in the 3-dimensional vacuum case. In his 1982 paper. And then since then, there are various approaches, and they use spinor approach. And a complete proof using spinor approach was provided by Bike and Kushel. So that's for n equal to 3, and that's a spinor approach. And their method was generalized to higher dimension, directly assuming the manifold is spin. Which is a differential topological condition on n. So our proof is a different variational approach without the spin assumption. Which in 3 dimension also provide a different proof to the one provided by Bai and Kushel. Okay. And a second remark is, so as soon as I wrote down the statement, you may immediately come out the question, where the dimensional restriction come in? So the assumption A is used because we need positivity of mass. So we set up a variational problem to show on the positivity of mass, the matrix G and K with all those assumptions is a local minimizer. So we have to use the positive mass, the statement I'm going to write down. Which is done in our prior work with Mikhail Eckmeyer and Rick Shen. which says for N, G, and K, which I will usually refer then as initial data set, just a terminology. So if an initial data set satisfies the assumption, the first three assumptions, A, B, and C, and then we can conclude the energy has a lower bound in terms of the linear momentum. So the follow-up theorem is a natural question from that point of view, is we want to understand what happened in the equality case. So in general relativity, once we know you have this relation between E and P, then one can define so-called the ADN mass. Which taken to be Lorentzian norm of E and P. And so the formula can be, say, as my title suggests, there will be the positivity mass, and this is the equality when mass is 0. Okay. So this type of positivity mass has been studied for the past few decades. And there's a very, very important special case when K, the symmetry to tensor, is identically 0. So from this Lorentzian geometry point of view, that means we are looking at totally geodesic slice. But then this is important because if we think about K is 0, and then the dominant energy condition reduced to a purely Riemannian condition, which is non-negative scalar curvature. So from that, people also refer to as the Riemannian case. So, and then in the Riemannian case, it has been done 40 years ago. So this is a 40-year anniversary of Riemannian positive mass theorem. By Shen and Yao. So let's reduce to if we have a Riemannian manifold, which is asymptotically flat with non-negative scalar curvature. And then in this case, P, the quantity, the linear momentum P, is also defined using K, so that vanishes as well. So the stemma reduced to the ADN energy is non-negative. And with equality, only if the Riemannian matrix is flat, is Euclidean flat. So let's just take out in particular the equality case. So when the energy is 0, energy is just a number. So I haven't told you how you define, and I'm not going to write down the formula neither. But roughly speaking, so think this is a manifold M. And then once we have a Riemannian matrix, you can define a number correspond to it by compute some quantity along a large sphere. So codimension 1 sphere in N. So you come out number, and then you let the radius of the coordinate sphere go to infinity. So roughly speaking, that's just some number defined at the infinity of manifold. But then let's make the rigidity statement in particular very, very strong, because it tells you that becomes the energy, this number becomes abstraction from being able to bump up scalar curvature. So think about we are just in Euclidean space, and now we have a big 3-dimension solid ball. So we ask, can we have a matrix which is strictly positive inside the ball, but it still remain Euclidean outside? And this theorem tells you you cannot do that, because if you don't change infinity, the mass will always be 0. So this is a very striking, you can think about it as a scalar curvature rigidity phenomenon. So in some sense, in our theorem, we want to explore the similar phenomenon for the dominant energy condition, which is not really a curvature condition on n, but the formula look a bit obscure. That's from the space-time positivity. Some space-time curvature is positive. Okay. And also, I want to make some remark. So this rigidity statement in particular is a way to characterize Euclidean space. So people have asked a similar thing, whether they're analogous statement for, say, hyperbolic space or for spherical space. So there's analogous hyperbolic mass rigidity. So our proof also provide a proof which settle the remaining case for the hyperbolic mass rigidity. So which is in a preprint. With Hyun-Chul Zhang and Daniel Martin. So which is just, we handle the Riemannian case, but there are many, many known cases before mostly used spinor approach. And I also mentioned, so the corresponding question for spherical is more delicate. In particular, there's a striking example for the hemisphere, which is non-rigid. And that's an example provided by, actually a lot of examples provided by Randall and Fernando. And under names. Okay, so since from the Riemannian point of view, the rigidity question is closely related to scalar curvature deformation. So I want to probably first discuss how the scalar curvature deformation is related to the rigidity question. Okay. So we will probably looking at a stronger deformation result. So the rigidity tell you mass 0 is an abstraction from bump up scalar curvature. So now you want to ask, given a matrix, if you don't know what the mass at all, can you just bump it up locally in your compact set? Can it be down, or if there's any abstraction? So we'll look probably a little bit even stronger statement than just the mass rigidity. So there are various approaches, especially related to the prescribing scalar curvature. So there's one approach by Fisher-Marston. They use the functional analysis approach. They think about, let's view scalar curvature as a map. And we want to say whether the map is surjective. If the map is surjective, that means for any given function, it can be realized by the scalar curvature of some matrix. So we'll let R to denote the scalar curvature map. So this is a map from gamma, which will denote to be a Riemannian matrix. So it's a map that sends the Riemannian matrix to a function that's the scalar curvature of gamma.
Sorry, is there a space-time version in the hyperbolic case?
There is, right? And the rigidity statement is still open. Even But I have to make sure. Probably the spin, assuming spin is proof, but the general without spin assumption is still open, right? So what we done here is the Riemannian case. So even the Riemannian case is just recently be just solved, yeah? Because in hyperbolic case, for the general space-time positive mass theorem, the invariance is no longer 1 plus n. It's actually a matrix invariant. Yeah. Okay. All right. So let's back to the scalar curvature deformation. So we think about this as a map. And you can actually write down the formula, how it's defined using the, like locally, the matrix is a symmetric, positive symmetry to tensor. So you have a formula for the scalar curvature. It turns out it's a smooth map. So if it's a smooth map, what we can do is we can differentiate. So we want to understand whether the map is at least locally surjective. We want to look at the linearization. So which is just a fancy name to say the derivative of this map. And the functional analysis theorem tells us we just need to check whether the linearization is surjective. Then Fisher-Marston told us this map is probably a little bit harder to understand because this is a map acts on symmetry to tensors, so there are a lot of unknowns. So instead, they look at a join operator. Which I will denote by LG star. So LG star will be an operator which sent in the direction backward. So it's going to act on functions. And it actually has a quite nice formula. So given a function f, the two adjoint operator acts on the function f as a second order differential operator. So you will take the Laplace times the matrix because it's sent from function to a symmetry to tensor. And then plus the Hessian of f minus f times Ricci. So the idea is, so if the linearization is surjective, that means a joint operator should have trivial kernel. Okay. So when I was a beginning student, I was very confused. What does that mean, the formal L2 adjoint operator? Because the definition seems different from the real true adjoint operator from the functional analysis textbook. But until one day when I graded the calculus exam, so one student did integration by part and forgot every boundary term. So, so while he mastered the concept of formal L2 adjoint operator, I marked 0 on that question. All right. So what the kernel element looks like if we satisfy second order differential equation. So let's just look at an example. So we look particular on Euclidean space, Rn with Euclidean metric. So this operator becomes just the first two terms because the curvature is 0. So that's how a function can be inside the kernel. But then if you take a trace of it, and notice the trace will give you some multiple of Laplace, which has to be 0. So it has to be a harmonic function. But even stronger, you plug in back, that means the Hessian of the function has to be 0. So the only possibility is it can only be a constant function or linear function. Okay. So in fact, this is a general phenomenon. The kernel of this adjoint operator can have at most n+1 dimensions. So back to how it's related to whether we can bump up the scalar curvature just in the compact set. So there's a very beautiful result by Justin Covino. And what it shows is the no kernel assumption. So let's look at omega, which is a manifold with boundary. And then we are consider if we have a Riemannian matrix on it, and with the matrix has non-negative scalar curvature. And then what his result says, suppose the no kernel assumption holds on omega. Then for any then find compactly supported symmetric tensor H. So this is symmetric to tensor. Such that the scalar curvature of the original matrix plus the small deformation has strictly positive curvature. Larger. So he proved a more general statement, but the one relevant to the mass rigidity is under the no kernel assumption. Then you can find compactly supported symmetric tensor, which is a deformation of the matrix, such that if you compute the scalar curvature of this deformed matrix, it can be made strictly positive. Just see here is just technicality. You can make it strictly positive in a ball larger than the support of H. Okay. So then later combining with a conformal change argument, he can actually show if the mass is 0, then we know the matrix before you prove it's Euclidean, it must be the corresponding operator must have non-trivial kernel, just because you have the obstruction to bump up the scalar curvature. So, okay. So any questions so far? Yes?
You assume any growth on F?
Um,
You all to the flatness or?
Right, so it's a very good point. So actually here we don't need to assume any growth, because if you see this equation is actually overdetermined. This is a function, but you require the Hessian to have some certain property. So the solution of the function f actually uniquely determined by the first jet of f at one point. Because you can just compute this equation along any geodesic, and you know it's determined by the value and the derivative. So this trivial has no any condition, boundary condition. Yeah. Okay. So we want to study the analogous deformation problem for the dominant energy condition. So let's revisit what the dominant energy condition is. And also I will introduce some notation. I will also write abbreviately this dominant energy condition as DEC. Just is the name is too long to write every single time. So this coming from the condition on the Einstein, so-called Einstein constraint map. So if you haven't seen that before, you can think about it's a generalization of scalar curvature map. But it's a tensor value. So given an initial data set G and K, this map, denoted by capital phi, will send to a tensor value, and which the first component has a scalar curvature inside, but there's also other terms given by K. And then the second component, which will be the divergence K minus the derivative of trace of K. So if you stay this a little bit longer, probably you'll recognize this is very look like a Gauss equation, Kodazi equation. That's indeed the case. This coming from as a compatibility condition. If the initial data set can be in any space-time with the Einstein equation, as a compatibility condition, this equation should satisfy some condition, and which will be the dominant edge condition we write there. So for shorthand notation, this is a scalar value function we denote by 2 mu. And this is a one form. We denote by J. So using this notation, we can rewrite the dominant edge condition as mu greater or equal to the norm of J. So also keep in mind when K is 0, this should recover to the non-native. So this recover to the scalar curvature map, and this become the non-native scalar curvature assumption. So we thought about whether there's any abstraction to locally promote the dominant edge condition to make it strictly positive. So this question also come out in my joint work with Justin Covino. We try to do a Green construction. So if you have given 2 initial data sets with a dominant edge condition, can you produce a third one by interpolating in some nice way in between? So then for that purpose, we also need to understand whether we can perturb to make the inequality strict. So there is some analytical difficulty though. So the first one is if we want to think about this as a scalar value map, then one want to say we can differentiate looking at linearization. But then this term, because it's taken to be the norm, so it's a square root, and it's not differentiable. So we cannot differentiate. So this scalar value quantity is not differentiable. So there are some suggestions which we may work on this tensor value map phi. And look at whether the tensor value map phi is surjective, and then we can say reduce to this combination to be surjective. But it also, that approach is also not working. And why it's not working? Because surjectivity of phi means, roughly speaking, you are able to prescribe mu and j, right? Because if it's a locally surjective map, so you can prescribe mu and j, and then you will find out a deformed g and deformed k to realize that value. But then, see the right-hand side, the norm is taken with respect to the Riemannian matrix, which change as well. So there's a subtle balance when you prescribe J and how the G will come out. So in order to overcome this analytical difficulty, so Covino and I we introduce a modified constraint map which is exactly to be designed to absorb the error term from the change of the norm. So we denote to be phi bar is a modified map. So given initial data, say gamma and tau, this will be the usual map, but we modify by a lower order linear term. So the argument here is gamma and tau. The only thing changed is gamma and tau. And so this is only, the additional term is only depend on gamma here. And the J is lot of a fixed matrix G and K. So just to simplify this modification. So then we can prove analogous statement from here, which will replace the non-native scalar curvature by dominant energy condition. Oh, sorry, this should be 2000. Right. Okay. So combining with this result and then the original proof of the Riemannian case, it seems to suggest the following approach to the equality case for the general space-time positive mass theorem. So I will write as an attempt. So we will begin with the one which realized equality, as well as the dominant energy condition. And then using the deformation result, we know we cannot locally bump up the dominant energy condition because it's supposed this should be inside Minkowski space-time. So together with the conformal change argument, that means we cannot bump up the dominant energy condition. So that implied the kernel is non-trivial. Right. Yep, so what's the kernel? So let me backward a little bit, ahead of myself. Okay, so the constraint map, which have the same domain and codomain as the modified constraint map. So we can look at the original constraint map. So it stands from a positive definite symmetric tensor and a symmetric tensor to the space of function and one form. So the adjoining operator will send backward. So we can think about this is a map that sends a function and a vector field. To the pair of symmetry to tensor. Okay, so you can write down the map explicitly. So since the higher order term, the linear order term will be scalar curvature because the k will be the quadratic term. So when you linearize, that will be the leading order term will be the linearized scalar curvature. So the adjoining operator will have a leading order term. The term with highest derivative will also be the adjoint of a scalar curvature map, plus some lower order term, and there are 10 other lower order terms. And then for the remaining component on X, you can see for the map in K, this is also linear in K. So when you linearize it, the term will be leading order. Leading order will be lot, and adjoint will be the lead derivative, and then minus the divergence of X times G, and plus some lower order term. Okay, so this formula is more involved because that becomes a map from a pair of function and the vector field. But it still shares very similar properties as the linearized scalar curvature map. So let me probably give you a couple examples. So in the case when K is identical to 0, the Riemannian case, and all those lower order terms vanish. So this map becomes decoupled. So that's a separate equation for f and x. So the first one will be just adjoint of the scalar curvature linearization. And the second one will be just this term. Right, so this will be the Riemannian term, and this will be the other remaining equations. So this has to be 0. But then if you take a trace, you find out the divergence as 0 as well. So the equation reduced to this. F is satisfied this equation, and X is the Killing vector field. So this equation in some sense captures the symmetry of your manifold. So the follow-up example is we will probably try to verify it for Euclidean space, because this is the model case in the Riemannian situation. And then you find out the equation for F tells you, again, F can only be constant or linear functions. And then the X will be a Killing vector field on Euclidean space. So what are they? So that corresponds to the symmetry. They can only be translation and rotation. All right. So, and this tells you the kernel is finite dimensional. So you can have the dimension n plus 1. That's the dimension of F plus the dimension of X, which is n, and n choose 2. Okay. So that's for a very special case. But this dimension upper bound, it holds in general. So no matter what initial data say G and K, the dimension is always finite and bounded above by this number. Okay. And the last one is it actually been observed by Moncrief. The kernel element correspond to 1-to-1 to the space-time Killing vector field in the following way. So in this example, this is a Minkowski. So you have a translation as a space-time symmetry. But then you can decompose into the normal part and the tangential part. And the length of the normal part is exactly the f in the kernel, and the tangential part is the x in the kernel. So there's a one-to-one correspondence in the vacuum case. Okay. All right. So if we follow the original proof of Riemannian case, it seems to suggest the following approach to the space-time case. So let me write as an attempt. So we'll begin with initial data set with the dominant energy condition, as well as the equality. And then we know we can conclude the kernel must be, there's a non-trivial element because we cannot bump up scalar, we cannot bump up dominant energy condition. So that means we have the abstraction. So there's a kernel element. So it looks like we get additional equation on the manifold we can work on. But then one still wonder, what does the kernel mean? And we know in the vacuum case that corresponds to space-time symmetry. But here in the non-vacuum case, this is a modified operator. It's a different operator. So we don't really know what the kernel element is. So originally we hope to show the space is actually vacuum. Okay. And then this will correspond to a very active field called stationary uniqueness. So this will tells you this. So we are talking about in the category of stationary manifold. And then another hope is once we know it's vacuum, we can use the classification of stationary space-time. Because now we will have a space-time which is rigid flat and which has a Killing vector field. So the hope is there are not too many. We want to see whether we can classify it and see this must be Minkowski space-time, correspond to the Minkowski space-time. Okay. All right, so this step is done by the deformation argument. And so when we work on this step, so you have the kernel element to imply it's vacuum, and we realize this approach may as well as prove so-called the Barnick stationary conjecture. Okay. And then at least implication, this step will correspond to a full classification. Barnick stationary conjecture is related to his quasi-local mass program. So if you have a manifold with boundary, you want to extend to an unbounded manifold which is asymptotically flat, and then compute what's the energy and momentum. And he claimed the one which realized the minimum of the energy and momentum is stationary, vacuum stationary. And this classification of stationary space-time is also sometimes called the uniqueness of stationary black holes. So it's a very active field, has been studied for many decades, and the more recent development has been done by Ionescu and Kleinemann using wave equation type. So we're very excited related to all those open conjectures. But it's very unfortunate. We found an alternative proof before we can prove either conjecture. So I will probably use the last few minutes to describe our alternative approach. But it does help because when we realize the relation to Barnick's conjecture, and we learn a proposal given by Barnick, which is an idea how to solve a kernel element with prescribed asymptotics. Right? So again, we begin the one initial data set with equality. So the goal is to find a kernel element, not just by the general deformation argument, but moreover, we want to be able to prescribe how it behaves at infinity. So this asymptotic look a bit weird, but this, roughly speaking, if this in the vacuum and the corresponding time-like Killing vector, the corresponding Killing vector field will be point to no direction. Okay. All right, so what original deformation argument enables to do the first step, but we will not be able to specify the asymptotics. If we can specify the asymptotics, then we can avoid the full classification of stationary space-time. And once we can prove that, there's also argument by Bike and Crucial. It will imply E and P are both 0. Okay? So the way we solve this equation now becomes a variational. So we will set up a functional. So this is a functional on the space of initial data set. Okay. And work on the Euler-Lagrange equation of this functional. And it turns out it's the nutshell of this proof is by exploiting, when you do integration by parts, what's the leftover of the boundary term. So that's really the difference of this formal adjoint operator and the true adjoint operator. Okay. So let me just write down the functional and probably tell you the property, how it can be done. So we will define the functional to be, also we will fix a given function f and a vector field, which we can make it arbitrary but fixed and equal to E and minus P outside compact set. So this will be fixed, and then the process will tell you we can find out a lower order error term to correct this function to make it satisfy the true equation. So the function is defined by, we compute what the energy of the initial data set and times the E, which is a given number, and then the momentum of the initial data set, that product with the given constant vector, and then minus an integral term, which is a modified map, integrate against the given function. So the first claim is the Euler-Lagrange equation of this will come out exactly this adjoint operator. So in some sense, the map is by design. So when you differentiate, when you linearize it, for the integral term, you will linearize the modified map. But then you want to put all the integral to the other function and the vector field by integration by parts. But then the boundary term will come out because we are not looking at the compactly supported deformation. And then the boundary term will cancel out exactly the deformation of those quantity. And the second claim is unfortunately, G and K is not a minimized, is not a critical point of this functional. Because if it were critical point, that means the first derivative has to be 0, then we just trivially find out F0, x0 solve the adjoint equation, which cannot be right because they're just arbitrary function. So the second claim is, although G and K is not a critical point in general, but it is among some suitable constraint. It's not only critical point, it's actually a local minimizer. Okay. So last, in this step, we use positivity of mass. So the key thing which we solve this particular constraint using the modified operator, because we know for gamma tau satisfy this equation, it has to satisfy the dominant energy condition. So that means we have control on these two quantities. And just by simple Cauchy-Schwarz inequality, we know it will give us this quantity will always be greater or equal to 0, the first two terms, and it can be only 0, is 0 realized by at the one with equality. Okay, so then finally, the step is we use Lagrangian multiplier because it becomes a minimization problem among constraints. And then by the Lagrangian multiplier method, it produces a multiplier. And working out the functional analysis actually show the multiplier will goes to 0 at infinity. And then which together with that multiplier, the prescribed function and vector field will solve the true adjoint